Hello, we are trying to understand the behavior of systems like this that are constant coefficient second order uh, and have an oscillatory right-hand side. And so in this problem, we're actually asked to use some kind of computer-assisted system. If you have Grapher, you could use that. If not, then Wolfram Alpha on the web is a good resource where they have differential equation programs. And the focus here is to decide whether this system exhibits resonance or beats. So let's, I want to supplement that with a little bit of theory. Here we have the homogeneous solution, which is, think of this as x prime plus 1 over 2x. So the frequency is 1 over the square root of 2, or the item here is 1 over the square root of 2t. And so that's the homogeneous solution will be C1 times cosine 1 over the square root of 2t, C2 times sine 1 over the square root of 2t. And for the particular solution, we're going to guess something that has the same argument, 0.7t, as the right-hand side. So we're guessing some constant times cosine 0.7t plus some other constant times sine 0.7t. After we determine A and B based on getting the right-hand side, then we will determine C1 and C2 based on the initial conditions. And then I want to see whether we actually get resonance or beats. I'm expecting beats because 1 over the square root of 2 is 0.707. It's not the same as 0.7, but it's pretty close to 0.7. And so I'd like to see how that comes about, but we're expecting beats. Again, this problem originally asked you to check this out using some kind of computation utility, not the way I'm doing it. I'm doing it to complement the problem that I hope you're doing. Putting the particular solution into the left-hand side, we get this linear combination of cosines and sines. This from the second derivative, minus 0.7 squared. And this from just putting in the solution, and the right-hand side is supposed to be 3 cosine 0.7t. So let's see, the coefficients of cosine are minus 2 times 0.49, or minus 9.8a over here, plus a over here, so that's a times 0.02 on the left, and that's 3 on the right. And so multiplying both sides by 50, I get A is equal to 150 cosine. And the coefficients of sine on the right-hand side, obviously the coefficient of sine is 0. And on the left-hand side, I get 0.02 B. And so B has to be 0. So there's no sine term in the particular solution. So the particular solution is 150 cosine 0.7t. And then we have the homogeneous solution, or the solution to the homogeneous equation, constant times cosine 1 over the square root of 2t and constant times sine 1 over the square root of 2t will match the initial conditions with those. Solving for the initial condition, x of 0 equal to 1, x prime of 0 equal to 0, x of 0 is 150 plus C1, because the cosine terms are 1 and the sine terms are 0, so that's 1. And x prime of 0 comes just from the sine term, 1 over the square root of 2 from the differentiation, times C2. And that's equal to 0, so that means that C2 is equal to 0, so there's no sine term. And C1 is obviously 1 minus 150. So we get that the solution is 150 cosine 0.7t minus 149 cosine 1 over the square root of t. And to try to understand the beats, we try to understand this as the as having two components, one which represents how close 0.7 is to 1 over the square root of 2. And so let's rewrite cosine 0.7t as cosine of 0.7t minus 1 over the square root of 2t plus 1 over the square root of 2t. That's just combining one term, which shows us how close 0.7 is to 1 over the square root of 2, and then the other whatever we have to have. And cosine of the sum of two angles is cosine of the one angle times cosine of the other minus sine of the first angle times sine of the second. And so that allows us to rewrite this 0.7t in a way that shows us where the frequencies are close and where they're far away. And so we'll plug this into the solution and we will see what we got. Here's our final version of the solution to part A. We have combined the 0.7 minus 1 over the square root of 2t terms and the ones that involve just 1 over the square root of 2t. And the thinking is this: 0.7 minus 1 over the square root of 2 is pretty small, so that it takes a big change in t to go through one period, one cycle of sine. So this is slow, or slowly varying. So it takes a long period, a long time, for sine to go through sine 0.7 over minus 1 over the square root of 2 to change. And these are fast, quickly varying. And so that's the motion inside, if you will. So we have this slowly varying part, which will give us a slow kind of beat to it. And then inside we have this fast changing signal. So if you think of it in terms of sound, you have a rapidly changing note inside these beats that come every now and then. In contrast with what we got with part A, we're looking at another constant coefficient second order linear equation with an oscillatory right hand side that's a little different. Over here, if you rewrite this as x double prime plus 9 over 4 x is equal to 1/4 sine, but if you think of the homogeneous equation, it's 0. So you get x double prime plus 9 over 4x is equal to 0. Then the square root of 9 over 4 is 3 over 2. And so the homogeneous equation is going to be some constant times cosine 3 over 2t plus some constant times sine 3 over 2t. And sine 3 over 2t is exactly what we have on the right-hand side. And so we are expecting resonance. And in this case, if you think of it as an oscillator of some sort, then a spring, let's say, then it has a mass and it has a spring, but it has no damping, and the driving frequency, you think of this as a force acting on the mass, then the driving frequency is the same as the natural frequency, the frequency of the spring without the force. And so that's why we are expecting resonance. Let's look at it a little more technically. In this situation, because any cosine of 3 over 2t and sine 3 over 2t when stuck in the left-hand side is going to give us 0 on the right, we need to try a particular solution that has a t in it. So it's a times t cosine 1.5t plus b times t sine 1.5t. I've not written the calculations on the board, but let me go over them very quickly. If I take the first derivative of the particular solution, I'm going to get a, when differentiating t, I'm going to get a times cosine, and then when differentiating cosine, I'm going to get a times minus t sine, and then of course the 1.5 in there. When I differentiate the second term, again it's a product, I'm going to get b times 1 times sine, and then I'm going to get bt times the derivative of sine, which is of course cosine, again times 1.5, the derivative of the inside. Anyway, you can see that I'm getting cosine and sine terms as well as terms that involve t. When I differentiate it the second time, the exact same rule will apply. In the end, I'm going to get at times something that gives 0. I'm going to get bt times something that gives 0. And then I'm going to get some terms that are not 0 in the left-hand side. And that's going to allow me to get sine of 1.5t on the right. Having calculated that and having plugged in the initial conditions into the particular solution plus the homogeneous solution, I get this final answer, 1 minus t over 12 times cosine. You can see this t over minus 1 t over 12 obviously is coming from the particular solution. The 1 is coming from the homogeneous solution. And then 1 over 18 sine 3 over 2t. Obviously, b in the particular solution turned out to be 0, and c2 turns out to be 1 over 18. Anyway, there we have it. We have the frequency of the solution is the same as the frequency of the right-hand side. And this first term increases in size, right? The second term, the absolute value of this is at most 1 over 18. But the absolute value of this first term increases with t. And that, again, is what we call resonance. And again, this is the theoretical calculation for this equation. We were actually asked in this problem to do an analysis using some kind of graphical system or some kind of numerical solution system. But I wanted to explain the theory that distinguishes between resonance and beats.